Perfect. So yeah, hi everyone. For all of you who are either attending live or who will watch this session on YouTube later on, welcome to the Multimodal Weekly webinar series hosted by the team at 12 Labs. For context, we've been running this series on a weekly basis every Friday at 1:30 p.m. Pacific time. And here's some of the topics that we tend to cover each Friday. Can be news research in foundation models and multimodal AI, from interesting application of multimodal and Gen AI in different verticals. Since we focus a lot on video, we also sometimes have folks talk about their video projects, and sometimes we have team members internally talk about our documentation platform and APIs. So here's the list of some of the recent speakers and the talks that we got over the past few weeks or so. So you can see we have a wide range of folks with background in research, industry, startup founder, open source developer, etc. and all. And so for the session today, we'll have the two speakers coming from both the research and academic background, as well as more like from the industry and production point of view. The first half of the webinar will be a presentation coming from Jacob Buckman, currently the founder and CTO of Manifest AI, and he will give a talk on linear transformer. And I got a chance to watch his talk in person just a few weeks ago at an event also in San Francisco that basically exploring different alternative architecture from transformer. So excited to have him here with us to evangelize this concept of linear transformer more to a broader audience. And then on the second half of the webinar, we'll have Rohit Agarwal, currently the co-founder of Portkey.ai. I also got a chance to watch his talk recently at an event focused a lot on essentially productionized foundation models, not language model in the industry, and Rohit will go a bit deeper on techniques, infrastructure, tooling that enable enterprise as well as industry organization to bring these big foundation models into production. So yeah, that's the agenda for the webinar today. And as usual, let's just note here, feel free to send your questions in Zoom chat, as you watch, and the speaker can answer them either asynchronously after they finish, or we'll have a short Q&A session about like 5 minutes or so after each speaker finish. Yeah, so with that, I stop sharing my screen and I will let Jacob to share screen and get started with this presentation. Let me know if there's any trouble with sharing screen.
Yeah, give me just 1 second here. I gotta go through system preferences. Sorry. I might have to quit and reopen. Apologies.
No worries.
Oh, no, I think it's working actually.
Perfect.
All right. Thank you so much for having me, James. I appreciate the opportunity to come and, as you say, evangelize a little bit. Really, it's just an opportunity to talk about something that I'm really excited about, some work that I'm doing together with my colleagues at Manifest AI on coming up with new architectures for large language models that are faster than transformers. And the title of this talk is Linear Transformers Are Faster After All. I'm going to start off by talking a little bit about why transformers are in some sense slow, why linear transformers might seem to be faster, why empirically in the past, people who have looked at linear transformers have actually found them to be slower, and how, in some recent work that we've been doing, we've shown that actually linear transformers are faster after all. So with that, let's get started. I want to start off by just framing the problem a little bit, which is something that you may or may not have encountered depending on how heavily you've been using ChatGPT or similar systems, which is that there's a fundamental limitation to the amount of tokens that can be processed sort of all at once by one of these large language model architectures. And this is actually a fundamental limitation. It's something that is deep in the training process, that they're only able to reasonably use the amount of tokens that they've been trained on. So let's go a little bit more and see why this is. I guess I should mention that the reason why it might be important to overcome this limitation is that there's plenty of applications you could think of that require processing a lot of tokens all at once. For example, looking at an entire medical record or collection of medical records, looking at an entire live news feed, like a fire hose processing AI. These are situations where we're looking at like a security log, which is logging all sorts of stuff and then checking it for anomalies. These are applications where you really just want to be able to handle a ton of tokens all at once, and they'll need better architectures in order to be able to do that. And let me explain why. So the motivating task here is language modeling. This is sort of the goal that GPT-4 is trained for. GPT-4 is what underlies ChatGPT, so we're going to use that as sort of our motivating task here. It's a very straightforward task. The input is going to be a number of tokens. In this case, I'm assuming tokens and words are the same, although they're not always in practice. The input we're going to call the context. And in this case, we're going to denote it by T in these slides. So here T would equal 9 because there's 9 words being fed into the neural network, which is being represented as this black box in the center here. The output is then a distribution over possible next tokens, right? And this is how language models work. It's basically just extremely fancy and powerful next word prediction. So the first thing I want to bring up is, in what sense does a transformer have quadratic cost? And this is why transformers are slow, by the way. Transformers have quadratic cost when the best models could have linear cost. And I'll go into a bit more detail on what exactly I mean by that. So a transformer looks at each token in the context before making a prediction. So it should be clear from this, the cost of one prediction is big O of T, right? You're going to be doing some amount of computation on each token. Now, if we want to make a prediction on each prefix of a sequence of length T, the cost becomes O of T squared. And this is also very obvious. First, you want to look at the word to and predict what comes next. Then look at to be and predict what comes next, etc. You can imagine doing this during sampling, right? It's pretty obvious why you would need to do this. You're generating one word at a time. It turns out that during training, you also want to make predictions in sort of the same way. To effectively utilize a context of size T, each gradient update to the network requires making a prediction on each prefix of length T. So in that case, in both of these cases, you're going to be doing computation that's structured like this, and you're going to be paying O of T squared computational cost in order to process this transformer. So what is computational cost? Well, it translates into either hours. If you have a fixed number of GPUs and you want to wait for them to complete the computation, you have to wait for more hours. Or if you want to do that computation in a fixed amount of time, you have to spend money and buy big O of T squared GPUs. And, this means that for even like reasonably long context, it's completely intractable to train, because nobody on the planet has enough time or money to wait T squared hours where T is something like, 1 million, right? It's just not going to happen, especially not for a reasonably large model as well. So where can we find a cheaper alternative? A place that we decided to start looking at Manifest AI is right next to transformers. And this is just motivated by the fact that transformers are the one thing that we are 100% sure works really, really well. It's so well proven empirically. We figured that we might as well start looking for subquadratic architectures that are as similar to transformers as possible. Now, we're not the only people looking at subquadratic architectures, and linear transformers are not the only game in town when it comes to subquadratic architectures. You might have heard of other models like Mamba or Hyena, state space models. So there's tons of other lines of work that sort of start in different places and are after the same goal of a subquadratic architecture that still has performance similar to that of the quadratic costing transformers. But linear transformers is what we work on. It's what I'm most excited about, and it's what this talk is about. So that's the one I'll explain. Here in the top line, you can see the equation for a transformer. If you've worked sort of on the model training or maybe even model fine-tuning levels, you'll be familiar with this. There's these 3 things called queries, keys, and values. The details of what they are isn't necessarily so important, but what is important is the difference between the 2 equations I'm showing you here. And it just comes down to one thing, this exponentiation. So the formula for a regular transformer is doing this softmax. I'm ignoring the denominator here, but you're doing a softmax over the relationship between keys and queries. With a linear transformer, you remove the exponential, and you just now have a sum of the product of these 3 terms. And what this means is there's now a linear relationship between the output and any one of the keys, queries, or values. That's why we call it linear transformers. And B, it means you can write it in this special formulation, which we call the state formulation. Now, I'm not showing the algebra here, but it turns out this is equivalent, and we have the details on our website if you're interested. This also has been shown in many papers. I think the earliest one was even in 2016. So this is a well-known fact that you can write it in this recurrent formulation. The state refers to this variable s, and it sort of summarizes all the keys and values that have come before at any given point in the sequence. Now, because you can write it in that recurrent formulation, you can get away with paying the computational cost of an RNN. Now, unlike a transformer, which we said looked at O of n things each time, an RNN just looks at O of one things each time. Concretely, it looks at the next token, as well as this thing called the state. I have written as S whatever here, which just contains all the information that came before. So by passing information through the state across multiple time steps, an RNN is still able to potentially access anything that it has seen, any of the tokens it has already seen. But whenever it sees a new token, it just pays O of one costs, 2 inputs and 2 outputs. That means that make predictions on prefixes of a sequence of length t, which again, remember, that's the setting where transformers have cost O of t squared. The costs for an RNN will be O of t. So, all right, are we done? All right, transformers are dead. We went from O of t squared to O of t. Obviously not. All right, there's 2 major questions that got to be answered before we switch from training our large language models with transformers to training them with linear transformers. The first is, does the improvement in big O translate into practical speedups on realistic hardware? Just because we're doing fewer computations doesn't mean that we're doing them faster. The second question we have to answer is, was the removed exponentiation important to learning, right? We did change the formula a little bit, and it's possible that this new model does not learn, or importantly for deep learning, does not scale nearly as well as the original architecture. So the talk is going to start by addressing this first question. Do we get speedups on practical hardware? So we implemented each algorithm and benchmarked the speed on H100. Lower is better here. So we want less time, right? The results for sequential algorithms are exactly what big O analysis predicts. A sequential algorithm meaning one that doesn't really exploit the hardware very much. It just does each computation one at a time. But we can see the expected result, sequential attention grows quadratically, whereas the sequential state-based algorithm, this recurrent formulation, grows only linear. So it's always faster. But we don't actually want to be training linear transformers in a sequential fashion. We want to be training them in a parallelized fashion. This is how you use the GPUs. This is sort of the point of GPUs, is that they can do these massive, highly parallel computations. Now, fortunately, parallel algorithms do exist for both the attention and state formulations. Here you can see sort of my little sketch of what these algorithms look like. For the attention algorithm, which is the one that, again, regular transformers use to train, you basically lay out these big matrices in memory, and then do a giant, highly parallelized matrix multiply, which sort of breaks down the matrices and computes each piece of them on a different warp of the GPU, then reassembles it at the end. There's also these fancy algorithms like flash attention, which avoid actually materializing the big matrices in memory. And so that actually saves you a ton of both like memory utilization, which means you can train much larger and longer context models, and also actually saves you a ton of time because you have to transfer things in and out of the fast cache memory of the GPU versus the slower memory of the GPU much less frequently. The parallel version of the state algorithm is what's called an associative scan or a prefix sum, very common algorithm in computer science, where basically you're breaking down the sum into pieces, summing up each thing with its neighbor, and then in the end, you actually have accumulated the whole cumulative sum at the end by cleverly doing these combinations. Now, what does it look like when we train models using these parallelized algorithms? And fortunately, we do see massive speedups as expected. Here, the solid lines are the parallel versions. You can see it's like a multiple order of magnitude speedup, not even close. And the scaling appears to be the same. It's just way faster. I should mention that for the attention algorithm here, we are showing flash attention. So we're showing the even faster version of the attention algorithm. But what happens when you put these two graphs together? When you compare the parallel attention to the parallel state algorithms? Again, these are the ones that we're going to be wanting to use in practice because these are the ones that would actually be fast. You actually see that the fact that attention is so much better at utilizing the GPU more than makes up for the fact that it has to do way more individual computations, all the way up to around, in this case, 100,000 tokens. And that's actually more tokens than anyone commonly trains models on, especially in academia. Not some of the data sets will be larger than 100,000 tokens, but context length of 100,000 tokens at a time as input to the prediction people are rarely going that high or even beyond. And so this result is the reason why so many people who have looked at linear transformers in the past have dismissed them. They say, oh, it's fast in theory, but it's slow in practice. We actually prefer to use flash attention. This is why. It's because, there's just this massive, massive gap at any context lengths that people have been trying in the past. So one thing we might say here is, okay, the whole problem is that they haven't been doing long enough context training to really see the advantage of linear transformers. And that's true to an extent, but turns out we can actually do much, much better. There's a different family of algorithms, which we call chunked algorithms, that actually give the best of both worlds. So I'm not going to go through the details of exactly the equation, but this equation here is once again equivalent to the other two formulations. Attention, we have state, and now we also have chunked. The intuition behind the chunked formulation, you can see again my little sketch off to the right. We break up the input sequence into what we call chunks. We use attention within each chunk. So this is the fast algorithm that lets us really utilize the hardware, but has an O of n squared cost. We do that within each chunk. And then we use the state approach to combine chunks, meaning that we're always only doing O of n work overall, assuming that we choose small enough chunk sizes. So this, in the end, takes O of t total compute, like the state formulation, but leverages heavily parallel matrix multiplies, like the attention formulation. We get the best of both worlds, and the empirical results pan out. So we see that the parallel chunked algorithm is strictly better than both of the other algorithms at all context length. Not only is it as fast or faster than regular parallel attention, by the way, this is still using flash attention. We've squeezed every bit of juice out of the baseline we could. And the parallel chunked implementation is actually also using a custom kernel here. So it's also doing something flash attention like. And we see that not only is it as fast or faster than parallel attention at all contexts, it also scales just as well as parallel state. So even as the context length grows larger, it maintains its advantage. So now, finally, we've answered the first question. Does linear transformer formulation allow us to get practical speedups on realistic hardware? In the affirmative. But we're not done yet. Got to move on to the second question. Was remove exponentiation important to learn? From here, we've got to plot some scaling laws. And unfortunately, we don't see as rosy a result. In this case, we actually see a bit of a gap between the performance of the two models. The good news is the gap doesn't seem to be growing with model scale. So they do seem to scale about the same goodness with respect to increasing model size. But why is there that gap there? Why do linear transformers do meaningfully worse than regular transformers across multiple scales? So we investigated this question and we found what we actually think is a fairly satisfying answer. It comes down to the context scaling laws. So what this means is we could take a model and we could train different context length versions of that model. And what we find is that regular transformers on the left seamlessly handle larger context, right? As you're increasing the context side, there's no degradation in performance. There's just an improvement in performance and then what appears to be saturation. And this mostly comes from the data set we're training it on. We didn't use a data set that has good long context dependencies. So of course, we're not going to see continued context size scaling as we continue to make that context size larger. But you look at the right and you see a very different picture. Linear transformers seem to struggle as you make the context larger. Not only do they not get better, they get actively worse. There's instabilities. You can see these crazy loss spikes popping up, as well as the performance just getting worse and worse over time. And this turns out to actually be the primary source of the gap. When you use a very small context like 256, it turns out that regular transformers and linear transformers basically perform the same. It's only when you start to introduce longer and longer contexts that the linear transformers start to struggle and we start to see this gap. The previous plot that I showed, this was actually all at context size 1024. And by this point, there already is, as you can see, a somewhat meaningful gap. So what's going wrong? The intuition here is that classic transformers can be understood as having a constantly growing state, whereas linear transformers have a fixed size state. That's because classic transformers are basically remembering each and everything they see, whereas linear transformers are summarizing that information into a fixed size. After seeing enough tokens, the memory of a linear transformer starts to overflow its fixed size capacity. And this is why you start getting these instabilities, performance starts to degrade, et cetera. So there's solutions that us and others are working on. One of them is just scaling up the state size, so it essentially has more capacity. Another is using gating to allow the model to forget information, so it can throw out stuff that's no longer important, freeing up memory for new stuff that it can include. And I wish I could show you a complete solution to this and say, linear transformers have replaced transformers, but they haven't yet. These are still problems that we and others are working on, and you'll have to stay tuned if you want to hear the end of the story. But I'm very optimistic. I think that the preliminary results are looking really good. These massive speed ups on real practical hardware are super important. And my guess is that if not by the end of 2024, certainly by the end of 2025, everybody who is training foundation models and most people who are fine tuning them will be training the linear variant of transformers using the fast chunked algorithm instead of the slower attention algorithm on classic transformers. And yeah, if you like this talk, have any other questions, are interested in working with us or even just discussing these ideas, I love to receive emails. Here's my contact info, and yeah, also happy to take questions right now if anyone has any. Thank you.
Awesome. Thanks, Jacob, for the fast delivery of the talk. There was just one immediate question on the chat by Igor. He was asking, I think he's referring to the chunk algorithms here. Is this the same as the chunk-wise inference from retentive network?
Yes. Yeah, it's essentially the same. Some minor differences, but the core idea of breaking it up into chunks and doing, one fast algorithm across chunks and a second algorithm with better hardware utilization, but more flops within the chunk, that core idea is also there in RedNet. There's several other papers too. If you go to our website, manifestai.com, we have a blog post version of this talk, and you can see a full list of other people working on similar related ideas towards the bottom.
Yeah, I think I link it on the first page. I link it on the chat already, so folks can follow along, check out some of the references that you included. Maybe one question from my end is, what do you think about the applicability of linear transformer for multimodal problem with, let's say, audio, video, etc.? What's going to be like the implication of this architecture for those kind of modalities?
Yeah, so something that I think is really promising is the use of sort of sequence models to handle things that are maybe not immediately clear as sequences. So one example would be video, which can be seen as a sequence of images. But another maybe less obvious example is really large images, which can be seen as a sequence of smaller images, right? Just like taking little pieces one at a time. And in both of those cases, fundamentally, you encounter the same problem, which is that if you break it up into enough pieces, then training a transformer on it just gets really, really slow. And so I actually think that it's very likely that the first video models that become possible will be based on capable of watching a full movie or something, end to end, will be based on by just pure necessity, a linear architecture.
Yeah, that makes a lot of sense. I guess maybe dig a bit deeper into kind of your background, your motivation for doing research on linear transformer, and also studying Manifest AI. I think a little bit of research on your publication, your Google Scholar, and it seems that you have some experience working on from reinforcement learning to latent space model to optimization of data set, right? Or wide ranging of different more theoretical question in machine learning, right? Can you maybe give a high level summary of your research background? What led you to focusing on linear transformer?
Yeah, absolutely. So I've been in all corners of deep learning. I actually started off working on natural language processing and large language models. That was my sort of first foray into deep learning. This was back in 2016 or so. And from there, I then got into various adversarial examples, generative adversarial networks back when that was cool. The adversarial attacks on, for example, classification networks. And then I, for my PhD, transitioned more into reinforcement learning, which I love reinforcement learning as a research area, but it's something that is not ready for the prime time. You know, it's not something that's ready to build a product around. So in the end, as sort of like towards the end of my PhD, started getting back more into sort of my roots, looking at large language models and just generally deep learning models, training them at scale, thinking about like really what can this technology be pushed to do. And this was research I did together with my co-founder, Carlos, who is a longtime collaborator of mine. We first met working at Google Brain back in 2017 and have been basically collaborating on various projects ever since. And so one of the things that we really strongly believe and inspired us to start Manifest AI was that the deep learning tech has basically proven itself. You know, it's been essentially 8 years of continual progress, people making hypotheses, testing them, and we actually have a very good empirical understanding of what deep learning is capable of, even if we don't have a solid theoretical backing yet. And one of the things that we think is very clearly capable of is for like sufficiently easy prediction tasks, given enough data, and also given enough time and compute to process that data, it's able to solve them, right? And in this case, we think that a good way to remove the air quotes from sufficiently easy, it's sort of a good working definition of sufficiently easy, is something that a human could do. To us, this is the lower bound of what these are capable of, because we know, for example, humans can't factor large prime numbers in their heads. And for that reason, we don't make any claims about neural networks being able to factor large prime numbers, even given massive amounts of compute and data to train on. Maybe with like truly unfathomable amounts of each, but not anything that would be really practically possible. But human processes, something that, you know, you could hire someone to do, something that a person might do reflexively without even thinking, like noticing objects or producing speech, any task that is, you know, capable of being conducted within the confines of a mere human mind, we think can definitely be also captured by a sufficiently scaled up neural network, but not with current techniques. There's some stuff that's missing. And the most important thing that's missing right now is essentially, it's about the input to the network. The multimodality is one part of this, and context size is the other part of this. And in the end, if you want to really be able to capture sort of all tasks, you need to be able to feed in input that's comparable to what a human sees. And the human, you can read a whole book, you can read a whole library worth of books. You can keep debugging and debugging and debugging, keep scrolling through log after log after log, and you're not going to eventually run out of memory, right? You're not going to eventually forget what task you were even trying to do in the first place. And humans can also process text, video, audio, like all sort, I mean, like proprioceptive, touch, taste, right? There's all sorts of input signals that humans are receiving, and oftentimes for tasks you need to be combining many of these. So essentially, the thing that we feel is the biggest and most important research challenge tackling the field is to construct a model that can both process any modality and scale. So all of this stuff is only relevant if it can be trained at scale. So it's like a computational engineering problem. And if it can learn once scaled. So this is more of a statistical learning theory problem that it actually needs to keep improving with increased data. So I'd say that's the high level vision of what we're aiming for at Manifest AI, and the reason why we're starting our research here at Linear Transformers, looking for something that can at least first solve this one part of the problem of longer and longer inputs without being bottlenecked by this insane quadratic cost.
Yeah, awesome. Thanks a lot for walking over like your background, the story and the motivation for starting a company. And yeah, like I think highly resonate with that notion of designing models that model human signal, right? And you know, tackling both the problem both from an engineering point of view with reducing context size, but also more from a statistical approach of modifying the architecture. Maybe just one final question before moving on to Rohit is, I know you guys, I mean, still pretty early, but I know Manifest is hiring, right? Like researchers, engineer. Do you want to give any plug or anything for just like the kind of people you're looking for, you know,
yeah, absolutely. Yeah, right now, our team is still very small. we just have 3 core technical team members and some supporting team members as well. We're planning to keep the team small. We're focused. We're all very well versed in research, mathematical background is very strong, engineering, and also sort of like experimental, the ability to run and execute experiments and communicate the ideas. So if those things are skills that you have as well, and if the mission that I just described resonates with you and you're interested in working with us, please reach out. Yeah, would love to talk to you.
Awesome. Thanks a lot, Jacob, for that conclusion. Awesome. Rohit, do you want to get started with your screen sharing and your talk?
Absolutely. 100%. Thanks, Jacob, for that. I think I was hooked on and constantly looking up stuff on the site. And I think that was a brilliant presentation. I'm looking forward to all of the work that Manifest AI actually does. Some really cool stuff that's happening here. Awesome. So I'm going to specifically, I think, change gears a little bit and focus on production success. So how do we use LLMOps specifically for taking POCs to production? Quick intro, I'm Rohit, I'm the founder of Portkey. We are an LLMOps company. No prize for guessing that. And I'm going to talk you through what are the major challenges, production success that we are hearing from a lot of enterprises that are taking their POCs to production now. What are some possible solutions? And I'd love to take you through how we're solving it with Portkey. But most of these concepts can also be applied directly if you're building something yourself as well. Awesome. Great. So LLMOps for production success. So usually this is where we start. We have a lot of conversations. There are some great ideas that come across at a hackathon, and we've built an awesome GenAI app. We're ready. This seems to be working across our test set, and we're now looking to scale this to existing users or maybe to a completely new set of users. But then you run into seemingly simple problems, right? I just got rate limited. And I was doing this talk at an event with about 50 people sitting around. And I was just asking these questions saying, have you seen rate limiting issues? And almost everybody was like, yeah, exactly. The minute you start to scale, you have to worry about rate limits. But then another model just launched. And given that we're doing multimodal, I think there are so many new developments happening in the multimodal space that constantly new models are coming out. And you're tempted to try it out, but you have to go back and probably fix a lot of your software development lifecycle. So what do? Once you start to get into production, you'll also start to worry a bit about costs. What's causing these spikes? How are users using our LLM applications? How do we start to manage user credits? And then you get into, how do we manage usage-based pricing, tokens, API calls? There's a lot of monitoring involved in that. Your prompts need to be edited collaboratively. The prompt is basically the highest unit of, the piece where you can bring out the highest percentage of change in the result by just improving your prompts. But then somebody could edit it, and that's causing now an edge case, and some of your users are seeing not the right outputs. In fact, if you think about this entire theory around prompts are just code, it's important that you keep code almost sacrosanct. So how do you start to version prompts, do integrations and tests on prompts, and then make sure you're deploying with confidence? Similarly, I think, how are users liking our responses? Are we accurate enough? And these can seem to be very vague questions, especially in the AI realm. What does accuracy even mean? What does hallucination even mean? How are users really liking our system? Because that's the actual business value. The metric is, did users find value from the application that we built? And that correlates much better to accuracy, hallucination, performance than any other metric that we sort of measure. And then finally, this is like everybody's goal, right? How do we keep getting better? The AI models keep improving over time. Frameworks are getting better over time. And we have amazing new developments like Manifest coming up, where people are really pushing the boundaries of what's possible. How do we keep up with all of this? And these are almost all of the questions that people are facing as we're using these LLM APIs to build our own production level applications. And here's what I hear from almost everybody, right? So you have this POC bliss, you're enjoying it, it's lovely. People are just like, oh my God, this is going to be the next big app. And the minute you step into production, it's just, you're dealing with problems that have nothing to do with your application really. These are just operational challenges. And I like to think of it like this. The production challenges that we all talked about, these are actually product and engineering challenges. These challenges have nothing to do with your application really. They're all, and if I take an analogy from the traditional engineering world, these are all DevOps problems. And engineers aren't suited to solve all of these problems because I need to build my application, not solve these operational challenges. And that's where LLMOps as a category emerges and makes this transition from POC to production really, really smooth. I'm going to show you how we do this with Portkey. But as I mentioned, a lot of these concepts could directly be translated into something that you're building out on your own as well. Portkey is actually the two-line code upgrade that fixes this. The architecture of Portkey is built in a way that you actually insert these 2 lines. So if you're writing, if you're integrating, say, with OpenAI, you switch out your base URL, add your Portkey provider, and that's it. Portkey will actually end up now routing your requests something like this. So Portkey essentially is a gateway that sits in between your application and the LLM providers. And this thin layer, which adds extremely low latency because we're deployed on the edge environments, can actually provide all of this complex observability, model management, experimentation, security, testing, evaluation on this small thread. And your application can continue to keep getting better here, while you don't have to worry about the latest, greatest model that came out. How am I leveraging fine-tuning to the maximum, etc. The actual architecture is a little more complex. I'm guessing this is a technical audience, so you can actually take a look at how a production application will really be laid out if you were to lay out all of the different components of the operational side. Right? So have your business logic here. So you have prompt management and versioning, you have your context manager, you have your API keys, which are stored in a vault. This forms part of your GenAI service. This might also have frameworks included like LangChain, Llama Index, everything else. This is all the part of business logic that you should really be worried about. And then on the ops side, you have first the AI gateway, which is like a unified gateway where we are transforming the requests and responses. There's an observability layer, which is doing basic metrics like request count, errors, token counting, but it's also using derived metrics of evaluations and guardrails and safety, etc. So you're generating these beautiful metrics, and then you're passing them on to an observability store. The gateway also connects to an inference layer. This inference layer will have some amount of security, some amount of evals, and then the actual LLMs where the inference is actually happening. And all of this over time, you're passing data from your observability engines into your training area. And this could be, this is usually today is fine-tuning, where you're collecting important information, sharing it to a training set. That training set is continuously fine-tuning your model and is automatically updating it. So that's overall. So I did a disservice by compressing all of this into this block, but this block is essentially what Portkey is all about, which you can get started in a 2-line code change. And actually, you don't have to take my word for it. We've done this over 157 billion tokens that we've processed so far. Customers have experimented over 207 models across thousands of prompts. Right. Cool. So demo time. I'm gonna probably spend the next 10 minutes taking you through how this works in Portkey so that you get a real feel for it. And we can take questions quickly. I might not even take 10 minutes for the demo, but let's see. Awesome. Are you folks able to see my Jupyter notebook now?
Yeah, I'm seeing it.
Okay, perfect. So this is typically, if I were to comment out the Portkey pieces, and I've added some instrumentation to it. This is your typical OpenAI code, right? So you have your OpenAI key, and you're making a call saying, what's a fractal? I'm going to make this request on Jupyter. It's going to do its thing, and it's going to return a response. Should have used 3.5 turbo, but there. So we have an answer from GPT-4. Now, I'm going to say, no, let's start routing this request through Portkey, because Rohit, I want all of this beauty that you just spoke about, and I want to solve my POC challenges, right? So what I've done is I've added my base URL. The API key can actually be picked up from environment variables. And I've said this is make this call to OpenAI. And I'm going to make the same request. We're going to wait exactly the same amount of time that we waited the OpenAI call to return. There, we have an answer. No magic, right? But that's what we really wanted. Everything in your application stays the same. Nothing changes. But what's really happened is Portkey started to capture a lot of these metrics and give you insights into what's happening. What's happened is Portkey's actually captured your request and response. You can actually, configure who actually sees those logs. But this is the starting point. You're actually now starting to see what are your users requesting for and what is the response they're getting. If you prefer the full view, you have the JSON, but more often than not, you'll just want to see the pretty versions of it. Let's see how this actually looks in a real life application where you have requests happening across multiples of users and a lot of different models. Since this is by 12 labs, I like to just filter it down to maybe a multimodal model, right? So let's say I might have done some vision preview calls. So because Portkey supports every model that's out there in every modality, you can actually get these neat little request response pairs like this. So an example that I was trying to work with was, so I gave GPT-4 frames from a screen recording of my product. And I was asking it, hey, what screens are the users visiting and what did they do? So I just put in my screens, and then GPT actually came out with a response. Now, it was very easy for me to go through these logs and just quickly figure out what's happening, because there's this nice pretty view where I can actually replay the entire conversation. You can go trace by trace, or you can actually go request by request right here. Awesome. And I can just use keyboards to go through these applications really quickly. And if there are certain responses that I don't like, I can also just rate these. These are feedback that's fed into Portkey that helps you improve the system overall. But the aggregation's always most important. So if I go back to the last 7 days, I can actually see how much am I spending, how many tokens are getting used, what are the number of requests, and who are my top users, who is using the product the most. I can also check out how my error percentages look like, both across API errors or evaluation errors, to just get a sense of how confident are we in production. And you see all of this is happening from that 2-line code change we made. This is actually Portkey automatically inferring a lot of the information and a lot of the data. I could also pass specific metadata and get summarized aggregations over a lot of these metadata properties. So that's about observability, where I now usually, once you have this in production, you feel a lot more confident that you can now tweak things around to make improvements, figure out what's failing, and then make changes the right way. The way you can actually go a little bit deeper is with what we call as configurations. And these are gateway configurations. So think about how can I set up routing to multiple models in a very, very simple format. The most common example that we take is a fallback to Azure. A lot of times you might have an Azure deployment or an OpenAI deployment, and you want to fall back to another model whenever it fails. In Portkey, you would write it like this. You would say, retry 5 times, and then fall back from OpenAI to Azure OpenAI if OpenAI fails. And that's it. Now imagine the amount of boilerplate code you would have to write in your application for something like this, and then spend compute cycles in your server. Portkey could actually do this extremely efficiently within the gateway itself. Another popular example is, say, I want to try out a new open source model. So this model's come out, but I don't think I can test it on production effectively. So what you can do is, again, I'm going to retry 4 times, but load balance between OpenAI and the new Llama 2 model in a 95.5% setup. It's that easy. I have my load balance set up. 5% of my calls are going to go to Llama 2, and I can start to see how this is affecting my production playground or not. So this is a way you can effectively control the gateway. By just writing these short configurations, you can nest it as much as you like, and then start to see the impact of your application within a single pane of glass. The last thing I quickly want to talk about is the prompt library. More often than not, I've seen companies manage their prompt templates either in code or as text files that you're versioning on GitHub. Not really the best way to do it, because prompts are a special type of code, and there's so much more you really want to do with it. You want to collaborate upon it, you want to test it out, deploy version, and a bunch of these things. So Portkey provides this very handy prompt library where you can manage all of your prompt templates in a single space. So I could create something very simple like, let's take a Q&A example. And you say, so question, and then the user is going to give in a question. And you can create variables in Portkey as easy as this. That's it. I have my prompt ready. I can pick which is the provider I want to host it on. Let's try Mixtral. Okay. Set parameters as you like, and just generate a completion. Now think of this akin to the OpenAI playground, but that connects to any provider and any model in the world. What this allows you to also do is then you save it, and this is now ready for deployment. And when I say ready for deployment, what it really means is you could now use this prompt in your code as simply as this. So say prompts.completions.create, give it a prompt ID, pass in your variables, and it will start to do the same outputs. So what's happened is I've actually moved the prompt template out of my code base and into Portkey effectively with versioning. I could create versions, deploy them as well, etc. The latest thing that's in private beta that's about to launch really soon is how do you do fine tunes on a lot of this log data in 3 clicks? So that's something I'm happy to talk to you later about, and I know I'm running out of time, but I hope I've been able to cover a lot of the concepts on how can you actually prevent some of these production nagging problems by using tools like Portkey or building some of these concepts in your DevOps stack. I hope that was helpful. I'm happy to take questions. And if you'd like to just spend, talk more about LLMOps or your production environments, happy to talk about it as well.
Awesome. Yeah, thanks, Rohit. Thanks for working over the presentation, illustrating some of the key challenges and architecture design, as well as a live demo of the playground and some example as well. Yeah, for the audience, if you have any question for Rohit, feel free to unmute and ask them directly. I think like on my end though, I think like if it looks like Portkey is already supporting a lot of LLM providers in the market, right? I was browsing a little bit in the docs, and you see like a bunch of models already existing.
Yeah.
Do you only support like SDK, or you work also with API?
Oh, we actually support directly APIs. So Portkey has SDKs. We also work with OpenAI SDKs as well. But internally we actually open sourced our gateway sometime back. That gateway exclusively routes to different REST endpoints, making the SDK itself extremely thin. There's like 48 KB, and you can deploy the gateway anywhere you want. The gateway definitely has SDKs, works with LangChain, Llama Index, all of those players as well.
Yeah. It might be a bit self-serving, but we are Labs is about to release like a Python SDK sometime soon.
Okay.
So yeah, and also our API is publicly available. So we'd love to explore some potential like
absolutely
integration, with Portkey. I think there's a lot of value. Just like the example you show on GPT-4V in the demo, I think there's a lot of value to capture the raw input of the prompt plus the the video that they provided, then return the text output as well. I think that
Right.
will help our users a lot. We just have a lot of experimentation, capturing, see what problem works, and the results, the output.
Right. Yep. Happy to. I mean, I'd love to. And
Yeah.
because the gateway is completely open source, that's also something we could collaborate upon and launch it out much faster.
Yep. And yeah, and in terms of open sourcing the gateway, maybe just curious about like your experience with that. Like, did you see like any interesting patterns from the contributors? What is the thing that they have the pull request on, etc.?
Yeah, I think the number one pull request was exactly this: more models. I also want to support this particular thing. So I think expanding the integration support was something that all of our first pull requests were for. Of late, we're starting to see a lot more pull requests on deeper features. So one very requested feature was, hey, in the configuration, can I automatically also define timeouts? So the request doesn't linger onto an LLM for really long. So these are now very important, again, production use cases that are getting built into the library really quickly. And these are all coming from real world production examples. Saying I'm using GPT-4, takes too long. I want to interrupt the call and fall back to another model. So these are all, I think we're learning a lot from users on how they're using these different models. And I think starting to see a bunch of PRs there as well.
Yeah, and maybe just following up on this, and you don't have to share any like specific details, but like you support like a variety of different foundation models in the market, and you probably see the frequency, the usage pattern, right? Basically, what model is like more it's been utilized more than the other.
Yeah,
like from like there's a lot of content out there around this model perform better than the other in terms of like some leaderboard benchmark, academic benchmark.
Yeah.
But I think given your experience like with real research, can you share any like interesting insights from like the real usage of this model in production?
Yeah, absolutely. So I think we have almost observed a constant pattern of people starting with an extremely large capable model. So usually people will start with a GPT-4, or like more recently, they will start testing on Gemini Pro. But then over time, we've seen almost everybody settle down to a cheaper, faster model. So I think the most used model on Portkey still ends up being 3.5 Turbo because of its perfect value, right? It's extremely cheap, it's very fast, it's highly capable, especially if you've narrowed down on the use case. So if you've broken down instructions into simpler sets, then 3.5 Turbo works really, really well. So that's probably the most popular, that's the bestseller model on Portkey. I would say 6 months back, we would have said 95% OpenAI and 5% everybody else. Today, I see a lot more open source adoption where people are trying to go for smaller open source models that are self-deployed for specific niche use cases, which is where fine-tuning and better prompting becomes important. But that's a shift that we've started to see quite a bit. So I would say that OpenAI to everybody else has probably come down to maybe 70-30 now, which is significant because it's a big drop, especially in production usage.
Yeah, for sure. And we're closing up on the hour, but I think one last question from my end, because we're talking about fine-tuning open source model, right? And I think in the enterprise context, if I'm correct, there's like basically two approach here. You can fine-tuning a large model on your domain specific data, or the other approach is using RAG, which is I think like probably like a cheaper approach because you don't have to do a lot of like workflow coordination as well. Given some of your experience, like seeing some of the way people use between fine-tuning and RAG, like can you provide some insights on the pros and cons of the two approach for the listeners?
Yeah, I think one thing I do want to highlight is that fine-tuning it seems like fine-tuning is expensive, but given all of the platforms out there, fine-tuning's actually become extremely cheap now. So for say, and we've done fine-tuning for so many people now, 10,000 examples, the fine-tune would probably be $25, $30. So it's hardly anything, and you're getting something that's a little more niche. RAG is definitely way more popular. RAG plus fine-tuning gives you outsized benefits. But when to choose, I think it depends most of the times, but a core heuristic is we pick RAG for knowledge, we pick fine-tuning for format. So whenever you have style, format, form, those things you want to tweak, then fine-tuning is the better option. But if you're worried about knowledge, then RAG is obviously way more cheaper. You can control the kind of data, you can control the kind of outputs. So for enterprises, that's the balance that everybody seems to be striking right now.
Awesome. Yeah, thanks for sharing that insight. Super insightful. Awesome. Thanks for it. I think we're at the top of the hour now. So that's a great way to conclude our webinar. We appreciate both speakers today, Jacob and Rohit, for giving this presentation and sharing your insights on your respective domains, from designing new architecture to bringing these models into production. The recording of this session will be available probably sometime mid next week. So I'll be sure to post that on YouTube and share it with both of you, so you can get it to more audience. And yeah, as usual, we been running this webinar session on a weekly basis every Friday. So thanks to the attendees for joining today, and I look forward to have you guys participating for our future session. Thanks everyone, and I hope
Awesome.
you enjoy the rest of the session. Cheers.
Thanks a lot, James.
Thanks.
Jacob.
Thanks.